Welcome to this online training about external memory interfaces in Intel Agilex devices. My name is Steve. This training is available for desktop viewing, as well as in a format compatible with portable devices, both available from the same link included in your registration email. For either version, while watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. When you are done with the training, please use the link provided in the registration email you were sent to provide us feedback on the training and ways in which it can be improved. I'll remind you about that later. The main objective of this training is to get you familiar with the parallel external memory interface options available in Intel Agilex FPGA devices and how to implement them in your designs. You'll learn about the architectural features available in Intel Agilex devices that implement memory interfaces. The architecture is different from previous device families, so it's important to understand the underlying architecture to see how everything works and how external memory interfaces are built. You'll then get familiar with the design flow for the memory IP for these devices, named Altera EMIF FM. This includes simulation, timing analysis, and using debug tools to verify the correct operation of an interface. Here's the full agenda for this training. This first part covers the options available for implementing memory interfaces in Intel Agilex FPGA devices, the EMIF architecture, and the features of the hard memory controller. Subsequent parts of this training, available on the Intel FPGA training website and linked at the end of this training, discuss the design flow for the Altera EMIF FM IP, how to share device resources between multiple interfaces, and verifying and debugging an Altera EMIF FM implementation. As mentioned when you register for this training, it is highly recommended that you have previously watched the first online training listed here, or have experience with implementing external memory interfaces in other FPGA devices. The first online training linked here goes into detail on the basics of external memory and implementing memory interfaces in older devices that use the UniFi IP and the high-performance memory controller. The second linked training discusses memory interfaces in Intel Cyclone 10, Intel Aria 10, and Intel Stratix 10 devices. It builds on the information presented in the first training. There are some similarities in the EMIF implementation between the Series 10 devices and Intel Agilex devices, but the architecture and capabilities are different enough that this training is your best resource for an Intel Agilex implementation. For more detailed information about all aspects of the memory IP and implementing a complete memory interface, see the External Memory Interfaces Support Center and the memory IP user guides available there for each device family. It's a good idea to always have the EMIF IP user guide for your targeted device available. They are the definitive guides for every aspect of creating a memory interface using an Intel FPGA and will be referenced throughout the training. In order to implement a working external memory interface, here is a recommended design flow that includes all the steps involved. We'll come back to this flow at multiple points throughout the training. In this first section, we'll take a look at your options for selection of an FPGA device based on the external memory interface you've selected and the tools you can use to make this decision. Let's start by taking a look at the external memory solutions available in Intel Agilex devices. Intel Agilex devices support the memory types shown here, with their maximum possible frequencies and maximum transfer rates. Intel Agilex devices have the fastest DDR support, with clock speeds up to 1.6 GHz, with a maximum throughput of 3.2 gigabits per second. Support for additional memory types may be added in future releases of the Intel Quartus Prime software. As with previous device families, Intel Agilex devices feature completely hardened memory controllers to achieve maximum performance. DDR4 is implemented directly with one or more of these hard memory controllers. The other memory protocols make use of a hardened PHY, but still have a controller implemented using soft FPGA logic. One other option for external memory is high bandwidth memory. High bandwidth memory, or HBM, is currently in its second generation as a JEDEC standard. HBM2 uses through-silicon vias, or TSV, to connect up multiple memory die layers into a 3D stack. An HBM2 stack can provide up to 256 gigabytes per second bandwidth and run with clock speeds up to 1 gigahertz. Like external DDR, it uses a wide, parallel interface of 1024 bits, where each I/O provides up to 2 gigabits per second. Because of the large number of parallel signals required, HBM2 is implemented in an integrated device that includes the memory controller. Currently, HBM2 memory can be found exclusively in Intel Stratix 10 MX devices, but will be extended to Intel Agilex M devices. The HBM2 stack is implemented directly on the main device die using System-in-Package, or SIP, technology. Comparing the use of traditional external memory with HBM2, the FPGA connects to the external DRAM through traces across the PCB. HBM2 has a small footprint and low power requirements compared to traditional DRAMs, so it can be coupled directly to the host die, eliminating the need for external board traces and termination. You can see on the right how the HBM2 DRAM is located within the package and interfaces to the FPGA through an on-die interconnect bridge called the Embedded Multi-Die Interface Bridge, or EMIB for short. As already noted, HBM2 can support large bandwidths up to 256 gigabytes per second and can operate up to 1 gigahertz, making it the clear choice for meeting the memory bandwidth requirements for all next-generation applications. To learn more about HBM2 in Intel Stratix 10 MX devices, see the HBM2 page on the Intel FPGA website and register for the available free online training, linked here. For the most up-to-date information on memory support and performance for Intel Agilex devices, besides the Memory Interfaces Support Center mentioned earlier, see the main Intel Agilex page of the Intel FPGA website, linked here. To help in choosing what device to use and other decisions for the setup of your interface, there are a couple of useful tools available from the Intel FPGA website, linked to from the EMIF Support Center mentioned earlier. First is the External Memory Interface Spec Estimator. This tool allows you to filter on device families and external memory interface capabilities, features, and configurations. The result is a list of devices and configuration setups along with the maximum performance that could be obtained from that configuration. Use this to help you narrow down your decision on which device speed grade and memory configuration to use for your design. If you're at the beginning of the design cycle and trying to decide exactly which device to use based on external memory protocol and related options, try the EMIF Device Selector tool. In this downloadable spreadsheet tool, enter the number of interfaces you want to implement and the properties of the external memory you're planning on using for each interface. If you don't yet know what your interface setup will be, but you know the memory bandwidth you want to achieve, you can use the bandwidth tool as a starting point to see how many interfaces would be required to achieve the desired bandwidth. The tool returns a list of all the device family members that can support the selected EMIF configuration and the amount of device resources that will be required. Now let's take a look at the unique architectural features of Intel Agilex devices that are used to implement external memory interfaces. Compared to older device families, the I/O and memory hardware architecture in Intel Agilex devices is completely different. The biggest difference is that most of the interface resources are hardened. Previous families used a mixture of hard and soft logic resources to implement an interface. Much of the PHY interface in the I/Os and in the read and write data paths was hardened, but the controller and the calibration sequencer were implemented in soft logic. In these newest devices, the entire interface for some memory protocols, except for the user logic that accesses the memory, is implemented in hardened device resources. In previous device families, hard and soft resources available for other functions were configured to implement memory interfaces. In these newest devices, dedicated hard resources are specifically designed to implement EMIF. This includes faster I/O logic and a dedicated clocking architecture. These resources are already tuned and optimized specifically for implementing memory interfaces. All these new architectural features make it easier to implement higher speed interfaces, and they make it much easier to close timing. The first key difference in the architecture is how the I/O cells are implemented. In previous device families, I/O cells were arranged around the periphery of the device or in I/O columns. Devices that include high-speed transceivers had those transceivers placed on the left and right side of the device, and the rest of the I/O placed on the top and bottom edges. In Intel Agilex devices, the I/O cells are arranged in I/O rows at the top and bottom of the device. The I/O rows and transceiver block I/Os are numbered, so the I/O row on the bottom is 2 and the row on the top is 3. Each I/O row is split by a zipper block. This zipper block adjusts routing as needed for signals that cross over from one side of the chip to the other. The zipper is not specifically involved in implementing memory interfaces, but, as you'll see, the location of memory interface resources can be referenced with respect to the zipper. Each row includes all the resources needed to implement memory interfaces, as well as all other available general I/O related functions. Each I/O row is divided up into a number of I/O banks. Banks are designated in a similar manner to how sub-banks were referenced in previous devices, but now use the row number and a reference designator. So the second bank of I/O row 2 at the bottom of the device is named 2B, and the first bank of row 3 at the top of the device is named 3A. Banks are further divided into sub-banks. Sub-banks are designated as either top or bottom sub-banks. Unlike the designation for banks, the top and bottom designation for sub-banks refers to their placement relative to the edge of the device. So a top sub-bank is the sub-bank nearest the edge of the device, whether it's in row 2 at the bottom or row 3 at the top of the device. Each sub-bank connects to 48 I/O pins divided into 4 I/O lanes. Each lane contains buffer logic for standard single-ended or differential GPIO use, as well as SerDes and dynamic phase alignment circuitry. Each sub-bank also contains its own PLL and an independent hard memory controller block. The hard memory controller contains all the resources needed for implementing a memory interface in a sub-bank. This includes the controller itself, sequencer logic used as part of the memory calibration process, a DLL for read strobe alignment, OCT, and clock phase alignment circuitry. It's important to note that pins in the lanes of bank 3A are used for certain device configuration modes. Some or all of these I/O lanes cannot be used for an EMIF depending on the configuration scheme. See the EMIF IP user guide, available from the Intel FPGA website, linked to earlier and at the end of this training for details. Here is a close-up view of a single sub-bank. As you can see, each sub-bank has all the hardware resources necessary to implement a complete memory interface. I/O pins associated with the sub-bank are numbered as shown, with pin 0 in the bottom sub-bank's I/O lane 0 up to pin 95 in the top sub-bank's I/O lane 3. Any lanes not used as part of an EMIF can be used as general-purpose I/O. The paths in and out of the sub-bank allow for communication with soft logic and with other subbanks. These communication channels are the key to creating larger, more complex interfaces that require the use of multiple subbanks. It's important to understand the idea of adjacent subbanks. As we'll see in a moment, adjacent subbanks can be used together to create larger memory interfaces. Subbanks are adjacent to each other based on the blue lines drawn through the subbanks in the top and bottom rows as shown here. So, for example, the top subbank of bank 3A is adjacent to the bottom subbank of bank 3B, while the top and bottom subbanks of each bank are always adjacent to each other. In both the top and bottom rows of the device is a special block called the I/O Subsystem Manager, or IOSSM, located just to the left of the zipper. This block contains a hard NEOS 2 subsystem connected to each of the subbanks through an Avalon memory mapped interface. It is clocked by its own on-die oscillator, so it does not require a clock connection from a PLL. This subsystem is similar to the system used for interface calibration in older device families. The NEOS 2 processor executes a calibration algorithm at memory initialization time to account for skew between the data and strobe signals. As with previous device families, the algorithm figures out how much margin is available between the DQ and DQS signals, and then adjusts delays in the I/O to align the DQ signals with each other and center the DQS strobes. The sequencer blocks in each subbank perform the actual delay adjustment. The code for the calibration is hard programmed into the IOSSM block. Different steps of the calibration process are performed in different ways depending on the memory protocol being implemented. Each row has only one of these blocks, and each one is responsible for calibrating all the memory interfaces implemented in that particular row. The IOSSM block is able to calibrate multiple interfaces in the row, even if they are different memory protocols or running at different speeds. Note that since there is only a single NEOS 2 subsystem, the interfaces in a row must be calibrated sequentially. In older device families, multiple interfaces were calibrated in parallel with each other, since a separate calibration system was constructed in soft logic for each interface. A faster NEOS 2 processor and a more efficient calibration algorithm in these special blocks minimizes or eliminates the additional time required to calibrate multiple interfaces in sequence. The IOSSM block is a dedicated resource specifically for use with memory interfaces and may not be used for anything else in the design. For details about the calibration sequencer, calibration stages, and each stage's calibration algorithm, see the Intel Agilex EMIF IP user guide. As noted earlier, each subbank has its own PLL. Unlike previous device families, where the PHY clock tree spanned multiple I/O banks, the PLL and its clock tree only drive the I/O in the subbank where it is located. This helps minimize clock tree delay and reduce jitter. Any PLLs not used as part of a memory interface can be used to drive other logic. As we'll see in a moment, larger, more complex memory interfaces may span multiple adjacent subbanks. Since each PLL only drives the I/O in its own subbank, there must be a way to synchronize the clocking of each bank in a larger interface. This is done with a balanced reference clock tree. The reference clock tree is driven by a single reference clock, usually an input reference clock from the board. The reference clock tree feeds the reference clock to the PLLs in each subbank. The branches of the reference clock tree are balanced to ensure the reference clock arrives at each PLL at the same time. To further guarantee synchronized clocking between the subbanks, the memory IP makes adjustments to each PLL's parameters to make sure they line up. To help improve timing between the user logic and memory interface, every subbank also includes a clock phase alignment block. The PLL in each subbank is designed to clock the memory PHY, as well as to provide an output clock signal for clocking the user logic. The CPA block adjusts the clock going to the user logic to account for skew between the core logic and the periphery. This operation can help in easing timing closure for transfers between the core and the periphery. Besides the PLL-driven clock networks, a DQS clock tree evenly distributes the input DQS strobe signals for read capture. The distribution used depends on the width of the memory data groups. As we'll see in a moment, depending on the data width of the bus groups and the overall interface, one or more I/O lanes may be used. So, if the memory interface uses one differential DQS pair for every 8 DQ signals, as it does in by 8 mode, 4 pairs of dedicated input DQS pins on the subbank feed the strobes to each of the 4 I/O lanes in the subbank, represented by the blue arrows here. If a by 18 interface is implemented, 2 I/O lanes are required, so the 2 pairs of differential DQS by 18 inputs get distributed to 2 I/O lanes each. This distribution is shown in green. By 4 mode is also supported. 2 by 4 groups can attach to a single I/O lane. For this mode, 2 pairs of differential DQS inputs are routed to each lane, shown here in black. With the architecture just described, we can now examine how a memory interface is implemented. As mentioned, all the hard resources to implement an interface are contained within each subbank. Thus, a simple by 8 interface can be built using a single subbank and the I/O SSM block as shown here. When building an interface, there are a few important rules that, due to the hardened resources, make pin placement a bit more restrictive than in previous device families. First, in any interface, 3 of the 4 I/O lanes in a particular subbank must be dedicated to address and control signals. Larger or more complex interfaces may require all 4 lanes of a subbank. The generated output for the memory IP, discussed later, will indicate if 4 lanes are required. All of the address and command signals must be in a single subbank. They cannot span across multiple subbanks. The address and command pins in these I/O lanes have specific functions, so they must be connected correctly to the external memory. Their functions cannot be swapped with an I/O assignment. Besides the standard address and command signals for the memory, the AC pins include the input reference clock pins and an RZQ pin for calibrating the on-chip termination block. Any I/O lanes not used for address and command signals can be used for data groups. These signals include the DQS and DQS pound strobes, the DQ data pins, and the DM, data mask, or DBI, data bus inversion pins. In the example interface shown here, the address and command signals occupy I/O lanes 0 through 2, and the 8 DQ pins, the DQS pins, and the DM pin are assigned to lane 3. Use the reports generated by the EMIF IP, discussed later, to know exactly which pins to use. The remaining pin in I/O lane 3 cannot be used as a GPIO. The architecture of the I/O subbanks makes it easy to create larger interfaces. Larger interfaces simply use more adjacent subbanks. The I/O lanes used for the address and command signals must be in the middle subbank if the interface uses an odd number of subbanks. If the interface uses an even number of subbanks, the address and command signals should be in one of the 2 central subbanks to minimize latency when communicating with the other banks. As we'll see later, the only required manual I/O assignments for the data groups are for the DQS signals. The fitter can swap around the associated DQ signals in a group as needed. If no manual DQS locations are assigned, the fitter has the freedom to swap around which I/O lanes are used, as well as the DQ signals in each lane. If you want, you can still make manual subbank and pin assignments for the DQ and DQS signals using the pin planner or interface planner, formerly known as Blueprint. We'll look at the use of this tool later. In the example shown here, you can see that a 72-bit wide interface would require 3 subbanks. The data groups have been manually assigned to the 9 required I/O lanes, but these assignments could be removed to allow the fitter to select which group should be assigned to each lane. The fitter will honor the requirement of using adjacent subbanks and placing the address and command signals in the center subbank. Also notice that the memory controller and sequencer, discussed in a moment, and the PLL and CPA blocks in the middle subbank are all used by the interface. Control of the upper and lower subbanks is managed by the middle subbank, with only the PLLs in the upper and lower subbanks used as part of the PHY clock tree to balance the clock skew. Here's what the BY72 interface just discussed would look like placed into subbanks in a device. The faint red zigzag line highlights the adjacency of the subbanks. The red address and command I/O lanes are placed in the top subbank of bank 2A in the lower left corner of the device. Remember that the top subbank designation always refers to the subbank closer to the edge of the device, even along the bottom edge. With this compact placement, the top subbank of bank 2B is free to be used for any other I/O for the design or as part of another memory interface. All of the architecture and implementation details just discussed also apply to SoC device variants. SoC devices include a hard processor system, or HPS, based off of an ARM Cortex processor. An EMIF in these devices can be configured for use exclusively by the HPS or shared with FPGA logic. The same device resources are used. However, there are some restrictions on EMIF use with the HPS. First, only DDR4 interfaces are currently supported. Also, HPS EMIF interfaces are limited to a maximum width of BY72. If you are not using ECC, the maximum width is BY64. The BY8 mode for data group width is the only width supported. Finally, I/O subbank use is limited to only certain subbanks. These subbanks, located physically close to the HPS, are the only ones with hardwired connections to the processor. To implement the interface, you'll need to add a separate memory IP component to your platform designer system that includes the HPS. For more information about SoC device variants and more detail on the restrictions when implementing an EMIF for the HPS, see the Intel Agilex Device Handbook and the Intel Agilex EMIF IP User Guide. To learn more about Intel FPGA SoC devices in general, register for online or instructor-led training linked here. Now that we've looked at the I/O resources and architectural features for building a memory interface, let's take a closer look at the hard memory controller that you can use to control a DDR4 external memory. The hard memory controller found in each I/O subbank has many of the same features as the high-performance memory controller found in older device families. However, this next-generation controller has new features that make it possible to control DDR4 memory at up to 1600 MHz. The key features of the controller are listed here. Some features of note include a bypass mode to allow for custom controller use with the hardened PHY, and data width support for up to a 72-bit wide interface. The controller also retains and enhances many of the efficiency optimization features of the high-performance memory controller, discussed on the next few slides. Some additional features include bank interleaving, external memory ODT control, a number of memory refresh options, additional low power modes, and the ability to write and read the external memory's mode registers. The controller implements ECC with single-bit error correction and double-bit error detection. The hard memory controller has additional unique features for specifically accessing DDR4 memory. These include supporting the different timing parameters for subsequent accesses of either different or the same bank groups, and parity checks and alerts on the address and command signals. The controller also includes options for the chip selects on multi-rank LR DIMMs. Direct dual CS and quad CS modes provide 2 or 4 direct chip selects to access dual or quad ranked LR DIMMs, while encoded quad CS provides a 2-bit encoded chip select signal for accessing a quad rank LR DIMM. Finally, you can manually issue either the long or short ZQ calibration commands for calibrating the on-die termination of the memory. The long calibration command is typically used during initial device calibration, while the short command is used for periodic calibration adjustments due to changes in voltage or temperature. For more details on these features, see the documentation provided by your selected memory vendor. The hard memory controller is made up of the components shown here. The input interface on the left is connected to the user logic through an Avalon memory mapped interface. It accepts read and write commands from the user logic and returns read data and other information from the interface. The Altera PHY interface, or AFI, on the right communicates with the PHY, which in turn issues correctly formatted read and write commands to the external memory. Within the controller itself, a command path made up of the command generator, a burst adapter, the timing bank pool, and an arbiter manage the ordering and issuing of memory access commands to the EMIF. As we'll see in a moment, the controller can intelligently adjust the order of commands sent to the external memory to optimize performance. The timing bank pool keeps track of command dependencies and works with the arbiter to issue commands in the correct order. The controller is also responsible for maintaining correct timing for all operations. The global timer block handles the timing for activation of external memory banks, as well as managing bus turnaround when the controller switches between reading and writing. Finally, the data buffer control block manages the read and write data coming in and out of the data buffer. It ensures that write latency requirements are satisfied and performs data reordering as needed. Data reordering is another performance optimization feature we'll look at in a moment. To understand many of the efficiency features of the controller, it is useful to review the basic command cycle for DDR memory. Recall that rows in memory are in an idle state when not being accessed, refreshed occasionally to maintain the memory contents. Before a read or write can be performed, the controller issues an activate command to open up the location in memory to be accessed. The controller then issues either a read or write command. Once memory is activated, multiple reads or writes can be performed as burst operations to the same memory bank. When the controller is done reading or writing the memory, it closes the memory with a pre-charge command. The controller can also issue special read or write commands that include the auto pre-charge option, allowing the memory to close automatically on its own after performing the read or write. Many of the inefficiencies found in memory controllers have to do with the order in which the commands just discussed are issued to the memory. If the state machine on the previous slide was strictly followed, accessing 3 different memory banks would resemble the top waveforms shown here. Bank 0, the red bank, gets activated. Then, the controller has to wait before it issues a read or write command. the green memory bank needs to be pre-charged to refresh it and then activated again before it can be read. The blue memory bank also needs to be pre-charged and then reactivated. This sequential operation of the memory bank leads to a lot of idle time on the data bus. To mitigate much of this idle time, the controller implements look-ahead bank management. This feature efficiently reorders memory commands to take advantage of idle time. In the example shown here, the pre-charge commands to the green and blue memory banks are sent while the controller is waiting for the activation of the red memory bank. The activate command for the blue memory bank occurs after the green memory bank is activated. All the reads and writes remain in the same order. As you can see in the second set of waveforms, the data bus is constantly active and all three reads finish well before they would have without looking ahead. The controller can also intelligently keep rows open or close them using auto pre-charge commands, which avoids having to issue separate pre-charge commands. If it is determined that a particular area of memory will need to be accessed again soon, the controller will keep the memory open as opposed to always just closing the memory when it is done using it. This improves the efficiency for random data traffic. Another feature of the controller is additive latency. The external memory requires a minimum delay, named TRCD, after an activate command is issued, but before a read or write command is issued. With additive latency, a read or write can be issued internally immediately after an activate command, and automatically held by the controller long enough to meet TRCD. In this way, the controller doesn't need to hold the address lines for the entire TRCD period, and additional commands can be issued instead of waiting for TRCD. In the example shown here, the read command would normally not be able to be sent to the controller until T3 to meet TRCD, leaving T1 and T2 as no-op cycles. With additive latency, the read is sent right after the activate and issued to the external memory after TRCD. Additional commands could be issued to the controller at T2 and T3. The overall read latency is increased to 5, the additive latency plus the normal CAS latency after the read is issued to the memory, but being able to issue more commands in the interim is the main benefit. Additive latency can really improve efficiency when it is used along with bank interleaving. Bank interleaving is the ability of the controller to activate or pre-charge a bank while a different bank is performing a data transfer. The controller doesn't have to wait for the read or write command to complete before accessing a different bank. However, even with bank interleaving, the controller must still honor the TRCD requirement for when the read or write command can be issued with respect to the bank's activation. Additive latency mitigates this. In the example shown here, bank X is activated at T0. Without additive latency, the read of bank X, shown here at T1, could not happen until T4 after the TRCD timing requirement, which would push out the activation of bank Z. However, with additive latency, the read can occur immediately at T1. The activation and reading of banks Y and Z can also proceed one cycle after another. As such, after the initial CAS latency for retrieving data from bank X, the data from banks X, Y, and Z arrive back at the controller without any interruption between them. The controller's ability to perform additive latency along with bank interleaving take advantage of how DDR4 memory can be accessed while still meeting all external memory timing requirements. Besides reordering activate and pre-charge commands, the controller can reorder read and write accesses to improve efficiency. One of the biggest efficiency hits when accessing memory is switching between reading and writing different banks. Without data access reordering, this can lead to huge bus turnaround penalties, as shown in the top diagram. With data reordering, if the read and write operations can be reordered, the writes and reads can be grouped together. The turnaround when going from read to read or from write to write is much less than when switching between reading and writing. Grouping the reads and writes together minimizes the turnaround penalty. Along with interbank data reordering, the controller also performs inter-row data reordering. When accessing a different row in the same memory bank, an additional activate command must be issued. The controller must meet TRC, a timing requirement that defines the minimum amount of time between sending activate commands to the same bank. If data reordering is not performed, subsequent accesses to different rows in the same bank have to wait for the minimum TRC time to meet the requirement each time the row is switched. This can lead to many additional TRC delays. With inter-row data reordering, accesses to the same row in the same bank are grouped together, minimizing the number of TRC delays required. This, along with interbank data reordering, can significantly improve memory access efficiency. There are a couple of aspects of data reordering that are important to understand. The first is called command aging. This is a process to determine which command is sent to the memory based on how long it's been since the command was issued. For example, if a system has two or more masters accessing the same memory at the same time, the system's arbitration scheme will make the arbiter grant the older request and thereby minimize overall command latency. The second aspect to understand is called starvation control. The controller includes starvation control logic to limit the length of time that a command can go unserved. With starvation control, a counter is incremented for every command served. A starving command refers to a command that has not been served after a period of time. This will ensure that a waiting command is served as soon as the starvation counter reaches the specified limit. The starvation counter ensures that all requests will be served after the predefined timeout. This makes sure that low priority accesses will not get left behind while performing data reordering. Thus, command starvation support and control ensures that a command doesn't exceed the set latency requirements. For most designs, the hard memory controller and I/O banks form a completely self-contained hard solution for implementing an external memory interface. However, in some situations, it is necessary to add some additional soft logic between your user logic and the controller. These situations are listed here. If you are implementing an RLDRAM3 or QDR4 memory interface, the controller is implemented in soft logic when created with the Altera EMIF FMIP. The hard controller is only used for DDR4. Soft logic is also required if you are creating your own custom controller along with the hardened PHY. The hard local interface between your user logic and the controller is a native Avalon memory mapped interface. If the interface is set up as an ARM AMBA AXI interface slave, wrapper logic must be manually added to support ARM AMBA AXI standard features. Finally, if the ECC feature is enabled, the encoding and decoding are done using soft logic. The read, modify, write state machine, however, is hardened. The memory IP will add the soft logic for ECC automatically. This concludes part 1 of the training. If you'd like to continue the training, you can register for parts 2 through 4 for free at the links shown here. To learn about additional resources available to help you in implementing an external memory interface, continue to the next slide. There are many resources available to help you with memory interfaces in Intel Agilex devices. The documentation resources listed and linked here should be the first ones you visit. The EMIF Support Center and the EMIF IP User Guide are your one-stop shop for all things EMIF related. Besides documentation, there are many training classes available from Intel FPGA on memory interfaces, Platform Designer, and Interface Planner. The Platform Designer classes listed here will show you how to incorporate a memory interface into a complete system design. The Interface Planner online training goes through the basics of what the tool is and how it works, along with a demonstration of its use in the placement of an external memory interface. Intel FPGA provides many additional technical support resources besides technical training. Check out the online Intel FPGA forums. They're a great place to connect with other users to share experiences and find solutions to common issues. Visit the Intel FPGA Wiki for design examples and up-to-date articles written by field application engineers. Use the knowledge base to find solutions to the most common issues you may run into. Manage your software licenses and online training registrations using the Self-Service Licensing Center. Finally, for local assistance, contact your local Intel FPGA sales office to speak with a field applications engineer. One more thing. When you registered for this online training, you should have received a link to a short survey where you can provide feedback. We'd greatly appreciate it if you'd fill out that survey now. We're constantly updating and improving our training materials, and your feedback helps us create the materials that you want. Thank you for your feedback. My name is Steve, and I want to thank you for taking this training on high-performance memory interfaces in Intel Agilex devices.